If a diesel engine is to be operated within a certain speed range and under varying loads, a mechanical device is required to control the amount of fuel injected. This device is called a governor. The speed of a diesel engine depends on two factors: the amount of fuel injected into the cylinders and the load under which the engine works. Suppose, for example, that the engine is running at a certain speed. If the load is increased, the engine slows down. If, on the other hand, the load should decrease with no change in the amount of fuel injected, the engine speeds up. By regulating the amount of fuel injected, the engine speed may be kept within a certain range. To do this, various types of governors have been developed. Most governors operate on the principle of centrifugal force. Centrifugal force is the tendency of an object, when traveling in a circular path, to move away from its axis of rotation. These rotating weights are affected by this force. As the speed is increased, centrifugal force grows stronger, pushing the weights further away from their rotational axis. The distance from this axis is proportional to the speed of rotation. One type of governor is the overspeed governor. It acts merely as a safety device and keeps the engine from overspeeding or racing. The basis of the overspeed governor is a pair of flyweights mounted on the drive shaft. The outward motion of the flyweights is transmitted to a collar which slides on the shaft. The movement of this collar actuates a linkage to the fuel pump controls. A spring presses upward against the collar. As the engine operates at normal speed, the flyweights tend to move outward. This movement, however, is retarded by the spring. But should the engine speed increase to a point where the safe speed limit is exceeded, the centrifugal force of the flyweights becomes great enough to depress the spring. This actuates the linkage to the fuel pump control, reducing the amount of fuel injected, and a decrease in engine speed results. Thus, the overspeed governor serves as a safety device in preventing the diesel engine from overspeeding. One design of overspeed governor, called the overspeed trip, is sometimes used to stop the engine completely when a safe speed is exceeded. This type of overspeed trip has only one flyweight, also working on the principle of centrifugal force. While the engine operates at a safe speed, the rotating flyweight is held close to the drive shaft by a spring. As soon as the engine overspeeds, the flyweight moves outward and trips a latch. This causes the fuel supply to the injection valves to be shut off, and the engine stops. Let us repeat the action of this mechanism step by step. The flyweight is held to the drive shaft by a spring. When the engine overspeeds, centrifugal force overcomes the resistance of this spring, and the flyweight moves away from the shaft. In this position, the rotating flyweight trips the latch, which releases the spring-loaded plunger. The plunger pushes against the fuel cutout lever, which in turn moves the fuel pump control to the no injection position, and the engine stops. Before the engine can be started again, the latch and the fuel pump must be reset. This is done by this reset arm, which is mounted on the reset lever shaft. The fuel cutout cam, mounted on the control shaft of the engine, is used when stopping the engine by hand. When the starting lever of the engine is moved to the stop position, the cam turns the cutout lever, shutting off the fuel pumps. The regulating governor not only keeps the engine from overspeeding, but maintains the engine's speed at a fixed rate despite changes in load. In this governor, the flyweights are linked hydraulically to the fuel control assembly. This assembly consists basically of a piston connected to the fuel system controls, a housing, and a spring. The downward pressure of the spring is balanced by oil pressure on the lower side of the piston. The amount of oil in this space is regulated by a valve called the pilot valve, controlled by the flyweights. When the engine is running at a set speed, the port to the power cylinder is covered by the pilot valve plunger. The plunger is held in this position by the flyweights. If the engine load decreases, however, the engine speeds up, and the additional centrifugal force throws the flyweights outward, raising the pilot valve plunger. This opens the port, and oil from the power cylinder is now allowed to flow through the pilot valve cylinder into a drainage passage to the oil sump. The power spring forces the piston down, actuating the linkage to the fuel system controls, and the supply of fuel to the engine cylinders is diminished. As the engine speed returns to the set rate, the flyweights resume their original position, and the pilot valve plunger again covers the port. If the load increases, the engine slows down, and the flyweights move inward. This lowers the pilot valve plunger, allowing oil to flow through the pilot valve chamber to the power cylinder. This oil, supplied by a pump, is under a pressure sufficiently high to overcome the pressure of the power spring. The power piston moves upward, increasing the amount of fuel injected into the cylinders. Once again, as the speed returns to the set rate, the flyweights resume their central position. The gear pump, which supplies the high-pressure oil, is driven from the governor drive shaft and takes suction from the governor oil sump. A spring-loaded accumulator maintains a constant head of oil and allows excess oil to return to the sump. To increase the regulating governor's sensitivity and to prevent overcorrection, a compensating mechanism is used. This allows the pilot valve port to remain open just long enough for the engine speed to return to the set rate. A compensating plunger on the power piston shaft moves in a cylinder which is also filled with oil. When the engine speed increases and the power piston moves downward, the compensating plunger is also carried down, drawing oil from a cylinder below the pilot valve bushing. This creates a suction above the receiving compensating plunger, which is part of the bushing. The bushing moves upward, closing the port to the power piston. Thus, the power piston is stopped, allowing no time for overcorrection. As the flyweights and pilot valve return to their central position, oil flowing through a needle valve allows the compensating spring to return the pilot valve bushing to its central position. To keep the port closed, the bushing and plunger must descend at exactly the same speed. Therefore, the needle valve must be adjusted so that the oil passes through at the required rate for the particular engine. When the engine speed drops below the set rate, the actuating compensating plunger moves upward with the power piston. This increases the oil pressure above the receiving compensating plunger, which therefore moves down, carrying with it the pilot valve bushing. As before, the port leading to the power cylinder is closed. The excess oil in the compensating system now drains out through the needle valve as the spring returns the bushing to its central position. The governed speed of the engine is set by changing the tension of the speed adjusting spring. The pressure of this spring determines the engine speed necessary for the flyweights to maintain their central position. Oil, allowed to leak past the various plungers for lubrication purposes, is drained into the governor oil sump. These are the basic elements of this type of regulating governor. In actual operation, the events which we have seen step by step take place almost simultaneously. Let us review the operation of the governor in maintaining the engine speed under a suddenly increased load. The engine speed drops and the flyweights move inward, lowering the pilot valve plunger. Oil from the gear pump and the accumulator forces the power piston upward, increasing the amount of fuel injected into the engine cylinders. In the meantime, the pilot valve bushing has moved downward, closing the port in the pilot valve. As the engine speed returns to normal, the flyweights and the pilot valve plunger and bushing return to their central position. Now, if the load suddenly decreases and the engine starts to race, the flyweights move outward, lifting the pilot valve plunger. Oil drains from the power cylinder, allowing the power piston to move the fuel control, decreasing the amount of fuel injected. In the meantime, the pilot valve bushing has moved upward, closing the port in the pilot valve. As the engine speed returns to normal, the flyweights and the plunger and bushing again resume their central position. Always keep the governor clean and keep it free from dirty lubricating oil. Flush it out every 2 weeks with clean fuel oil. Flush it out every 6 months with carbon tetrachloride. Refill it with lubricating oil of the viscosity specified by the operator's manual. Be sure that the oil is always at the proper level, keeping it above 5/8 of an inch in the gauge glass. Never tamper with the governor unless you are positive that there is some trouble with it. And even then, all repairs should be made only by an experienced operator.